Hello, my name is Mihai Dusmanu and I will present an approach for privacy-preserving image features, a joint work between ETH Zurich and Microsoft. This work was sponsored by the Microsoft Mixed Reality and AI Zurich Lab. The main motivation for our work comes in the context of cloud-based computer vision systems. On one hand, there are several localization and mapping services, such as Microsoft Azure Spatial Anchors or Google's Visual Positioning System. On the other hand, Microsoft Windows Hello or Apple Face ID provide face authentication functionality. Let us consider the following application based on Azure Spatial Anchors. Users start by placing digital assets, be it markers or animated holograms, in a physical space. Later, these assets can be retrieved from phones, tablets, or HoloLens devices using visual localization techniques. The images captured by the user inadvertently reveal private information such as faces or license plates in public places and prototypes or other confidential information in private ones. For this reason, raw images are not uploaded to the cloud. Instead, feature extraction is executed locally, as underlined in Alex Kidman's article regarding privacy and ethical design. The traditional local feature extraction pipeline starts by finding interest points and estimating their geometry, scale, orientation, affine shape. Next, feature description takes as input normalized image patches extracted around key points and outputs a high-dimensional vector describing the appearance. Most state-of-the-art approaches use 128-dimensional floating point descriptors of unit norm. Recently, there has been rapid progress in feature inversion methods that reconstruct the image appearance from key points and descriptors extracted in the original image. This raises serious privacy concern since images might contain sensitive information about the scene or subjects. Similarly, researchers have proposed methods for reconstructing face images solely from their global descriptor. Moreover, they showed that the reconstructed images could even be used by an attacker to fool an authentication system. Increased awareness of these privacy issues has spurred significant efforts to develop privacy-preserving machine learning systems. Notably, in the field of computer vision, Speciale et al. Proposed to conceal geometric information by lifting 2D or 3D points to randomly oriented lines passing through the original locations. Subsequent steps of the localization pipeline use specialized solvers taking advantage of line-to-point correspondences. Recent works by Geppert et al. And Shibuya et al. Extend on the same idea to solve the full structure from motion problem. We draw inspiration from their approach, but instead apply it to feature descriptors to conceal the appearance information. The core idea of our work is to drop constraints from each feature descriptor by embedding it within an affine subspace containing the original feature as well as adversarial feature samples. Feature matching on the privacy-preserving representation is enabled based on the notion of subspace to subspace distance. Our approach adds plausible ambiguity to each feature, making it significantly harder for an attacker to recover private information. Let us first look at how to generate the affine subspace embedding. On the left side, we visualize a high-dimensional space. The blue cross represents the initial n-dimensional descriptor to be concealed, and the black smaller crosses represent other real-world descriptors. To define an m-dimensional affine subspace, one needs to provide a translation vector d0 as well as m vectors d1 through dm forming the basis of a linear subspace. During the first steps, we suppose the translation vector is equal to the initial descriptor d to make sure that the affine subspace passes through this point. One could sample random direction vectors for the linear subspace, referred to as random lifting. In our experiment, we found this approach to be vulnerable to relatively simple privacy attacks. The original descriptor can be approximated by the nearest entry from a database of real-world descriptors. This is because a random subspace generally intersects a single plausible region of the descriptor manifold. To address this issue, one can ensure that the subspace passes through multiple regions of the descriptor manifold. The basis vectors are chosen randomly according to a database of real-world descriptors. We call this approach adversarial lifting as it intentionally introduces plausible samples in the subspace to conceal the original descriptor. Moreover, a defender can choose adversarial samples to hide specific private information. To hide the gender of a person, one can pick a feature vector from another gender. Adversarial sampling improves privacy but reduces descriptor matching accuracy because the chance of accidental subspace intersections increases. Two distinct visual features might be lifted through the same plausible region of the descriptor manifold. To balance the accuracy and privacy trade-offs, we propose the use of hybrid lifting, where a subset of the basis vectors are selected randomly, while the rest are chosen using adversarial sampling. Finally, the translation vector can now be set to any point in the subspace, except for the vector D itself, since it is precisely what we must conceal. Thus, we sample a random point in the n-dimensional hypercube and project it to the subspace. Most applications also require feature description comparison, which is accomplished using appropriate pairwise distance measures. Given two descriptor points, a commonly used distance is the point-to-point Euclidean distance. Thus, in the following, we will restrict ourselves to the L2 norm. To compute the distance between a private descriptor represented as an affine subspace and the regular descriptor, one can use the point-to-subspace distance. The goal here is to protect the privacy of query images for a cloud-based localization service. The database images are supposed to use the original descriptors. This distance comes back to a simple orthogonal projection onto the affine subspace. Further, since the original descriptor is part of the subspace, the point-to-subspace distance is upper bound by the original point-to-point distance. Next, let us consider the subspace-to-subspace distance, which is useful for comparing two private descriptors represented as m-dimensional affine subspaces. Given 2 points D star E star in the two subspaces respectively, which achieve the minimum, a sufficient and necessary condition is that the line joining D star and E star is orthogonal to both subspaces. Under certain hypotheses, this constraint can be written in the following compact form. Thus, finding the subspace-to-subspace distance requires solving a linear system with 2m unknowns and equations. As before, this distance is upper bound by the original point-to-point distance. Please refer to the paper for additional details. Previous approaches to privacy-preserving descriptors take advantage of homomorphic encryption, which has the advantage of guaranteeing exact distance computation. In the context of local features, it is generally desirable to have at least 1,000 features per image. Obtaining the full distance matrix between two images would take around 16 minutes using the fastest most recent work on homomorphic representation search. This severely limits the practical applicability. In contrast, our method only induces minimal computational overhead, taking less than 10 milliseconds to match two images on GPU. This makes it amenable to real-time applications. As we cannot give any theoretical guarantees on the level of privacy preservation of our method, we empirically validate it using multiple privacy attacks. First, a nearest neighbor attack, which takes advantage of a database of real-world descriptors. Each private feature is approximated by its closest correspondence from the database according to the point-to-subspace distance. Finally, the approximated descriptors can be fed to a regular feature inversion network to reconstruct the appearance of the original image. Second, we consider a direct inversion attack where the affine subspaces are provided as input to a retrained feature inversion CNN. Note that the architectures proposed in previous works are very compute and memory intensive. training them on higher dimensional subspaces would be a challenge in itself. Using the raw descriptors, one can reconstruct the original image with very high fidelity. As previously mentioned, random lifting is vulnerable to simple nearest neighbor attack, while the hybrid approach is resilient due to adversarial samples. The direct inversion attack is able to reconstruct some parts of the original image, but the quality is significantly deteriorated. Furthermore, distinguishing details such as faces or text are heavily perturbed and become non-existent for higher lifting dimensions. For the mapping scenario, we integrate our private features into CallMap, an end-to-end structure from motion pipeline, and evaluate them on the crowdsourced local feature evaluation benchmark. For this evaluation, we preserve the privacy of all input images and use the subspace to subspace distance for matching. The private features come with accuracy trade-offs. As we increase the dimensionality of the subspace, the reconstruction completeness degrades accordingly. Despite the fewer number of registered images, the 3D models remain relatively accurate and clearly distinguishable. We also consider the case of localizing to an already built map on the challenging Aachen day-night long-term visual localization dataset. Here, we preserve the privacy of all query images and use point to subspace distance for matching. On the day queries, we achieve competitive performance even when lifting to 16-dimensional subspaces. Furthermore, even on the extremely hard night-to-day matching queries, where pose estimation has very low inlier ratios, we are still able to localize a reasonable number of queries. Moving on to face descriptors, the privacy attack we are concerned with involves inferring distinguishing properties from only the global features. For this purpose, we use a k-nearest neighbor classifier to predict the gender and race of a person. Using raw descriptors, this classifier achieves an accuracy of 86% on the gender task consisting of 2 classes and 52% on the race task consisting of 7 classes. All private representations using a database for lifting successfully conceal information. We also implemented a variant of our hybrid lifting, where each feature is lifted by sampling database entries with a different gender or of a different race to obtain a balanced subspace. This method achieves random level performance for gender, which essentially completely hides that information. Finally, we report face verification accuracy on multiple datasets based on state-of-the-art 512-dimensional arc face descriptors. The point-to-subspace matching performs within at most 2% of the original descriptors across the board. For the subspace-to-subspace distance, the performance on the simple datasets only drops by a few percent. For more complex datasets consisting of frontal-to-profile matching or large age differences, the performance drop is more significant. Nevertheless, the simpler datasets are still representative of common authentication systems, making our approach highly relevant for such scenarios. To sum everything up, we have introduced a novel privacy-preserving feature representation using affine subspaces. We propose a strategy for constructing affine subspaces containing adversarial feature points to make inverting the representation difficult. Pairwise feature comparison on the privacy-preserving representation is enabled based on the notions of point-to-subspace and subspace-to-subspace distance. The subspace dimension determines the trade-off between performance and runtime or degree of privacy preservation. We demonstrated the high practical relevance for the applications of visual localization and mapping as well as face authentication. Finally, directions for future work include improving the matching performance by using special descriptors or modifying the adversarial lifting protocol, and implementing scalable matching to enable large-scale applications such as place recognition. Thank you for your attention, and let me know if you have any questions.